Okay. Oh. Hey, Alana, can you hear me?
Yes, I can hear you.
Okay, good, thanks. Something is wrong with the camera and I cannot seem to fix it. So we're out of video again. Hmm. What the heck? Okay, great, thanks. All righty, do this.
We might not have the video, but we can see your screen, Dr. Howard.
Okay, great. Well, I mean, the camera is pointed at Melina and Dwayne, so I'm sure they're sorry that they're not getting their moment in the sun, but at least you can see the slides. Oops, and where do we get started? Let me do this there. Okay, well, let's let people trickle in as they will, and we'll get started on communities today. We're making the switch from two species interactions to talking about the nature of entire ecological communities. We were kind of hopeful back in the 1970s that we'd just be able to generalize those equations for predation and competition to to do kind of a community matrix where you had an equation for each species in the community, but it turns out that you can't really do that. And the reason, of course, is because it's really well illustrated when we consider the fact that the competition coefficients don't stay constant when you add or subtract other species from a community. So you can't just write a big old equation for a community, which is kind of what some people were hoping for. Ecology has a long history of physicists deciding that ecologists are making everything too complicated and they're going to make things much simpler. And so they come in with their mathematical ability and their equations and make a fuss for a year or two, and then they quietly leave the field when they realize that they were totally wrong about how complicated things are. Things, in fact, are really complicated. So today we'll start our consideration of communities by talking about these four topics, just what we mean when we say an ecological community. We'll talk about indicator species, and this will be the first of several terms that we will use to designate species that are important to a community in some way. Now, an indicator species is probably the least important of these important species, but nonetheless, it's a term that we need to understand because we talk about communities often in terms of a single species, an indicator species. We'll then examine the idea that communities could be open or could be closed, and we'll finish with a consideration of how we measure the most important thing there is about communities, which is community diversity, the number of species in a community and their relative abundance. Okay, you're going to have some practice problems to work on this. We only have a few practice problems left in this course, but this is one, and you'll have to do a diversity calculation on the fourth exam. So do have a look at that when it gets posted, and be sure that you understand how to do that. Now, I'll remind you of two things. For those of you in the lab today, your lab reports from 2 weeks ago are due, so let's get them in. I just want to try to get the lab back on some kind of schedule. We never got back to a schedule after the hurricane. So let's try to get those in reasonably soon. I will start penalizing late labs if you don't turn them in by 1 letter grade. The second thing is that in case you did not look at your email, I will not be here Monday. I'm going to post a pre-recorded presentation on food webs. I will be out all day, no office hours. And hopefully things will be back to normal on Wednesday when I would next see you. So with those two items out of the way, let's talk about communities. So when we talk about an ecological community, we're talking about an association of interacting species that coexist in time and space. So there has to be some physical connection to them. And an indicator species is a species that reliably and consistently predicts the presence of other species. That doesn't mean that it's really important for the functioning of the community. It's just that if you see this species here, you can pretty much guarantee you'll see certain other species. So a really great example of this is longleaf pine savanna, which is a globally threatened community. There's less than 1% of it left. It was only found here on the Gulf Coast. There are patches of it on the north shore of Lake Pontchartrain. There's some patches in Mississippi, including the Mississippi Sandhill Crane National Wildlife Refuge. There are some in Florida, including the Tall Timbers Research Station, but that's it. That's all that's left of an entire swath of the Gulf Coast, basically that went from the Atlantic coast north of Jacksonville all the way through Alabama, Mississippi, Louisiana, and into East Texas. It's all been destroyed. There's only those few remnants left. So longleaf pine savanna has a meaning to people who study communities. It is a savanna, that is, it is a grassland. It is a species-rich grassland. It has the highest species diversity anywhere in the world outside the tropics. So in an area the size of this desktop, roughly a meter square, you might find 50 different grass and herb species. That's astonishing. Okay, and those species are all predicted by the presence of longleaf pine trees, because they tend to like the kind of wet savannas that all this diversity is found in. So we call this community a longleaf pine savanna. There's no reason why we couldn't call it a Drosera savanna, because Drosera is another plant that reliably occurs in these areas. It's a pitcher plant, so it's an insect-eating plant. It's one of these things that has a expanded leaf that holds fluid in it that digests insects that fall into the fluid, and that's how they get their nitrogen. But Drosera plants are inconspicuous. Longleaf pines are hard to miss. You see a longleaf pine, you know what that is. The longleaf pine savanna then is a reliable way of indicating a particular kind of community. Okay. Now, you got to realize that this is another one of these things that we define for our convenience. The longleaf pine community doesn't have a fixed meaning. It simply means an association of organisms that tend to co-occur with this dominant, really obvious plant. Longleaf pines are, lovely trees, but they could just as well be slash pines or some other kind of pine. They don't have a particular significance for the rest of these species. It's just that they're obvious, they're large and obvious. And so an indicator species is something that we use to give a community a name when we're talking to one another about different kinds of communities. You will, in the next few lectures, hear about other species that do have an outsized importance in the functioning of this community. Longleaf pine, however, is not one of those species. You could replace it with 10 other different pine trees and nothing would change, really. Okay. Now, when we use the term indicator species, we kind of do imply that there's some consistency. And I just said that that's not necessarily true. Well, it kind of depends on whether we're looking at a closed community or an open community. A closed community has a distinct composition that is pretty consistent. And it has sharp boundaries when it butts up against a different kind of community. So it's easy to think of a closed community as kind of a discrete unit. Now, because these species co-occur together, and if you lose one, you lose them all, that's an indication that there are very strong interspecific interactions in closed communities, and that each species plays a specific and important role. And in the past, in the early 20th century especially, early ecologists analogized communities to organisms. They analogized them as superorganisms. So they made the comparison of the organ systems of the human body to the different species in a community. And they suggested that each of the species had a defined role to play. And that without that species, the community could not exist. So that was one point of view. And that was a common point of view up until the 1950s. Okay. The alternative, however, is that communities could be open. And in open communities, yeah, you got these organisms co-occurring, but there's no special relationships there. And they co-occur mostly because their physical environment requirements are similar. And that would mean that there are vague boundaries between different communities. And different communities might actually be mostly a matter of definition rather than discrete units. And the species distributions then would overlap, some would come in, some would fall out. And you might have the co-occurrence of a bunch of these species that you would call a community, but it doesn't have any particular significance. And what that would imply is that the interactions between organisms tend to be weak rather than strong. And in this case, species can easily substitute for one another. So it wouldn't matter. The whole community would not collapse if you removed one of the species. You could just plug a different species in. Okay. Well, this was a major controversy in ecology for about 30 years in the early 20th century. And here you see on the right the way that ecologists were thinking about them. So in closed communities, there is what we expect to be a very sharp boundary between two communities where all of the species of one community sort of stop and all of the species of the adjacent communities start within a very, very short spatial distance. And we call that an ecotone. So there should be an ecotone, a very sharp boundary between communities if we're dealing with closed communities. Okay, and so here's a gradient of some kind. We have no idea. This could be soil moisture or something, and this could be the dry end, and this could be the wet end. And you have 1, 2, 3, 4 different communities here. These closed communities then have very strong needs for wet versus dry soils, and they also have very strong interactions. Okay. On the other hand, down at the bottom, you can see our conception of open communities. So you see that the species distributions of each of these species is kind of independent of one another. They're kind of all over the place. Now, you could define a community right here on the dry end. And you might even pick this species here in the red line to be the indicator species. And it would be a community composed of 1, 2, 3, 4 species. But notice that when this species drops out, that has no bearing on the distribution of the other 3. In fact, this species here is distributed along most of the environmental gradient. So this then would be a real generalist, and this would be a much more specialized species. The community would just happen to have them coexisting in time and space. There's no special meaning to that. So the question then is, well, in real life, we have these conceptual models of what communities might be. What do real ecological communities actually look like? Well, long experience has taught us that most ecological communities are open. And so here is an example of communities that are open in space and communities that are open in time. So Harold Gleason, early in the 20th century, was the one who advanced this open community idea. And it wasn't until Robert Whittaker in the 1950s and 60s started actually mapping species distributions that we realized that Gleason got it right. Communities are not typically like superorganisms. They are kind of assemblages that we can say compose a community, but that's really for our convenience as ecologists when we're talking to each other about what to expect in a particular area. So there is a community that is called Cove Forest in the Smokies. It's generally found on the west-facing slopes of the Appalachian Mountains, and is limited to this area of eastern Kentucky. Okay, but is Cove Forest a real thing? As it turns out, no, it is not a real thing. It is an assemblage that tends to co-occur in the valleys of west-facing slopes of the Appalachians in this part of Kentucky, but it's not like it's a community with strong interactions. So here, what you've got, these lines define the distributional boundaries of a dozen of the most important species that make up the assemblage called a cove forest. And you see that some of them range as far north as southern Canada, out into Minnesota, and they have their southern boundaries somewhere here around the southern edge of Tennessee, kind of where Tennessee meets Mississippi, Alabama, and Georgia. So some of these species have a relatively northern distribution here. Other species have a more southern distribution. And they're limited in the south by the Gulf Coastal Plain and in the north by the freeze line. But they do tend to co-occur in this area of Kentucky with some of these more northern species. You have other species that are primarily western in distribution and overlap this way. And then you have some that have a relatively limited distribution in the east. But in no sense can you call this a closed community. These species don't depend on one another. They simply share physical requirements of the physical environment that happen to be met pretty easily in these west-facing valleys. So this cove forest community is something that we can talk about as ecologists, but we should not make the mistake of thinking that it is a thing that has some unambiguous physical existence. It is not. It is a term defined by the investigator. And where have we heard that? We've heard it when we talked about populations. A population is a grouping that is defined by the ecologist investigator. A community then is also defined by the people investigating it. So this is evidence in space that these species just happen to co-occur here, even though they're distributed spatially all over the eastern United States, and they don't even overlap. It's very clear that these southern species here don't have any real need or relationship with these other species. They can coexist perfectly happy without them. So it's not like there are strong interactions here. Here's a second example of evidence that shows open community structure, and that is the pollen record investigations of Margaret Davis. And what Margaret Davis did as a palynologist or pollen ecologist was to go to lakes around North America and drill cores into the mud, haul up those cores, date them using carbon dating and other methods if they were more ancient, and then ask, what pollen do I find associated with mud that was laid down at a particular date? If communities are closed, then you should always find the same kinds of pollen co-occurring together. If they're open, then all bets are off. You might find one type of pollen from one tree species that's currently found in a community, and you might be missing 99 others. And in fact, that's what she found. She found that pollen profiles were distributed completely independently. And what we think of as the modern eastern deciduous forest of North America, in fact, is just a bunch of species migrating in response to climate completely independently. So here's two examples. So here is maple pollen. And here is the number of thousands of years ago that it was found in these mud cores. So during the height of the Ice Age, 18,000 years ago, maples were limited to kind of what we think of as upper Mississippi and Alabama, and this southern area down here in Florida and Georgia. 14,000 years ago, this was the northern extent of maple trees. And then you can see that 13,000, 12,000, 10,000, they're moving north as the glaciers are retreating. Okay. And they reach their current distributional limit very recently, only a couple of thousand years ago. So at the time of Christ, there were no maples in Canada. They were all limited to this area south of the Great Lakes. And their appearance in southern Canada is very, very, very recent. Now, we think of maples as an essential part of the eastern deciduous forest, but in fact, they weren't there until just very recently. So you have this refuge down here on the Gulf Coast where maples waited out the ice age until conditions got better and then moved north. What's really remarkable and why we chose the second graph is because hemlocks are also a member of this eastern deciduous forest. They happen to be a conifer, but that's beside the point. But 14,000 years ago, they did not overlap with maples at all. Maples were here on the Gulf Coast, hemlocks were not. Maples and hemlocks have no specific relationship. Hemlocks were found during the ice ages in this coastal Carolina refuge right in here. And they waited out the ice ages here. And then they expanded to the west first, and then gradually moved north, sort of turned and moved north. But the movement of these species is completely independent over time. There's no necessary relationship between these species at all. This community is open in space, as we saw over here on the left, and it's open in time, as we saw here on the right. So open community structure is pretty much the rule in ecology rather than closed community structure. And we have good reason to expect that. Because what do we know about species that compete strongly, that have very high overlap in their niches? Yeah, I'm asking. Competitive exclusion. They're going to go, somebody's going to go extinct. So that's not going to persist over evolutionary time. What about really strong predator-prey interactions, where the predators are really efficient? They will cause the extinction of the prey. These strong interactions collapse, and only the weak interactions survive. What do we know about strong interactions and mutualisms where it's obligate for both partners? We know it's an evolutionary dead end. If one of the partners goes extinct, the other does. So the only thing that should persist over time are weaker interactions, and that's very consistent with the idea that communities should generally be open communities. That's also a really good thing for us, because we have destroyed so many elements of so many natural communities that we would be unable to reconstruct any sort of functioning ecosystem if we found that we needed to. And we actually, of course, do find that we need to do this. We need to reverse a lot of the damage that we've done. If communities were closed as a rule, we'd be out of luck. We'd be in a downward spiral to extinction because we would not be able to substitute one species for another and reconstitute the ecological services that we destroyed. But we can. The fact that most communities are open gives us hope. It gives us an opportunity to manage communities in a way that restore function in ecology and will allow us to persist on this earth. So that's a hugely important lesson. The fact that communities are open for the most part means that we have not put the bullet in the chamber and pulled the trigger. It means that we can reverse damage that we cause. So are there no closed communities at all? Well, not exactly. But we tend to find closed communities in very special situations where we have an environmental gradient that is very, very sharp. So we have an environmental gradient from dry land to open water. Well, there you have a changeover from terrestrial communities to aquatic communities. Okay, and terrestrial communities, by and large, will drop out very quickly once the soil becomes saturated. And aquatic communities will drop out very quickly once the soil gets too dry. So you should see a really sharp ecotone then between terrestrial and aquatic communities at the edge of a pond. So yes, we do see closed community structure. But think about the kinds of communities we're talking about here. We're not talking about different kinds of forests. We're talking about different biomes. So where you have a sharp environmental gradient that causes a change from one type of biome to another, you can expect to find closed community structure, sharp ecotones, wholesale species replacement over a very short spatial gradient. Now, it's easy to point out that ponds and dry land constitute one of these situations. There are others though, and they're often found on mountains where there's a temperature rainfall gradient that is extremely sharp. So over the course of a couple of 100 meters, you might have, if you think back to the regional climate lecture, a change from desert conditions to grassland conditions. And the species below would be replaced wholesale by grasses above, where it's cooler and wetter. That's another excellent example of closed community structure that's generated by a very sharp environmental gradient. If you think back to the Whittaker diagram of terrestrial biomes, desert is one biome, grassland is a different biome. As you continue up the mountain slope, you start to get forest. And that changeover can happen within a very, very short distance. And once again, you're changing biomes. So sharp environmental gradients can produce what look like closed communities, sharp ecotones, but unless you have one of those situations where you have a really quickly changing environmental gradient, community structure is generally going to be open. So here's a typical example of something that we face in trying to understand community structure. And here's some fish species that occupy either a river or an estuary. And the question then is, oh, wow, what kind of a model applies here? Well, look at the river fish. Look how they tend to peak at about the same point, and they tend to drop out very quickly in the salinity gradient. That looks kind of like closed. But look at the estuary fish. They're all over the place. And look, some of their distributional limits are way over here in salinity, and some are way over here. Hey, this is a typical ecological problem. The riverine fish look like they're more a closed community, and it's because they have very low tolerance for salinity. The estuarine fish look much more open. And there's kind of a sharp ecotone when you think about the river fish all dropping out at the same time, but the estuarine fish don't have an ecotone. It's a mixed model. It's more of a closed community for these river fish and more of an open community for these estuarine fish. So this might be Lake Pontchartrain here, and this might be the Tchefuncte River up here on the North Shore. But this is kind of typical of the kinds of problems that community ecologists try to analyze and try to understand what generates these patterns. What's generating this particular pattern is that the freshwater fish have little tolerance for salinity. The estuarine fish live in an area where there's variation from highly saline to almost fresh. They tend to have more tolerance for this. And so the rules that govern these two communities are different rules. The river fish tend to have tight boundaries. It's more of a closed community because they can't tolerate salinity. The estuarine fish have a more open community structure, and they are not so tightly bound by patterns of salinity. So this is just an example of how community ecologists have to deal with these things. Now, let's turn our attention to species diversity and spend the rest of our time talking about species diversity, because this is the single most important question in community ecology. How many species are in a community and why? Why does a community have a particular number of species? What regulates that? Well, one of the things that we have to do then, if we want to talk about this, is we have to define what we mean by diversity. And so we tend to talk about diversity in several ways, but there are two main ways we talk about it. The first way is what we call species richness. There's simply the count of how many species. How many species do you find in this community? How many species do you find in that community? Well, here we have two communities and they have 5 species each. Okay, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. But the other way that we talk about diversity is evenness, which is how similar the relative abundance of these species is. Okay, and so what you can see here from these two communities, in community 1, you have 25 individuals, but 21 of them belong to one species. In community 2, you have 25 individuals, but each species has 5 individuals each. These are equivalent in richness, but they are not equivalent in evenness. Community 2 is far more even. Okay, so the question is, which one would be more diverse, or is there a difference at all? And the best way to answer that question is to imagine yourself plunked down in the middle of community 1 at random, and with your eyes closed, and then open your eyes and look around. How many species can you expect to see around you? 1. If you were plunked down in the middle of community 2 with your eyes closed and then asked to open your eyes and count how many species you see, almost certainly be several. You might not see all 5, but you'd certainly see more than 1. For very real reasons then, finding a way to combine richness and evenness is an important thing for ecology, because community 2 is much more even, and in some very real sense, it is more diverse than community 1. Yeah, community 1 has these 5 species, but almost all of them belong to one species. The greater evenness of community 2 makes us think that community 2 should be more diverse in some real meaningful way. And if we're trying to make decisions about conservation plans, then the pattern of richness and evenness is really important. If we're looking for a place to set aside to preserve a threatened species, say species 1, the community 1 is just fine. But if we're looking for an area that is rich in diversity in general, then we'd skip species 1 and we'd choose community 2. And we would select that as an area for conservation. So there's a huge amount of effort in ecology trying to combine richness and evenness in some meaningful way. There is one dominant index that we use all the time to do this, and that is the Shannon-Weiner index. Now, this is just one of about 20 different diversity indices that we use in ecology. It's not even necessarily the best one, but it is really the most common one. I actually like a somewhat different method, better than the Shannon-Weiner index. But hey, everybody uses this, everybody. And so it's worth our consideration. So the Shannon-Weiner index comes from information theory. It was developed by these two guys, Shannon and Weiner, at the Bell Labs in 1945, trying to figure out how much information a telephone line could transmit. And then a guy named Weaver applied it to other information theoretic problems. And so sometimes you'll see Shannon Weiner, that's the original authors. Sometimes you'll see Shannon Weaver, that's the more ecological application. I just tend to call it the Shannon index sometimes. But this is what it is. So you have some species in a community. You have I species. Okay, so the Shannon index then is the sum of the proportion of species I times the natural log of that proportion. So if species 1 represents 10% of the community, then P sub I is 0.1. So it would be 0.1 times the natural log of 0.1. And then you'd go through the entire community for all however many species there are, all I species, and you'd make that calculation, and then you'd sum it up. Now, since the log of a fraction is a negative number, you want to, you'll get a negative total here, and so you want to change the sign so it's a positive number. So the diversity then is the sum of this, change the sign, and the higher than this sum, the more diverse the community. The more species there are adjusted for their evenness. Now, this ranges from 0 when there's only one species in the community to a high of about 4.57 or something is about the highest you can get. It actually asymptotes, where you have many species that are very even. But we'll get a practice problem or 2 or 3 posted on Moodle for you to work through this. But let's take our 2 communities and let's show you how we calculate the Shannon-Weiner index and show you that we can, in fact, use it to compare diversities in a meaningful way. So for community 1, where we have 21, 1, 1, 1, 1, here's the proportion of species 1, it's 0.84. So the Shannon-Weiner index is calculated then as 0.84 times the log of 0.84. And so that's the sum here, or that's the total here. And then for all other 4 species, they all represent 0.04 of the community. So it's 0.04 times the natural log of 0.04. And so that's this. So you get this 4 times. And so the total then is minus 0.662. You change the sign because, of course, it's a negative and you want a positive. So the diversity of this community is 0.662. This should be more diverse. And in fact, the fraction of each one of these is 0.2. Here's the natural log of 0.2. So this times this is this. And so you add them all up and the diversity is 1.61. 1.61 is greater than 0.662. Ergo, we consider community 2 to be more diverse than community 1. Now, the number is bigger. The absolute value by which it is bigger doesn't necessarily inform us of anything in particular, but it does tell us that by comparison, community 2 is more diverse by our weighting of richness and evenness. So there are other ways to do this, and here are a couple of others. Here's rank abundance curves. This is particularly useful, and I really like this method. Here's community 1, and 0.84 would be up here. So here's the first species, and then here are all the other species in the community. And they're way down here. And notice that you have a very sharp drop in the slope from 0.84 to 0.04. Species 2 has a very shallow slope. In fact, we've rigged it so that there is no change in the slope at all. It's a flat line. So look, if the slope here is steep, it means that one or a few species are numerically dominant and the others are all rare. If the slope is shallow, it means the species are pretty even in numbers. So this is a quick pictorial way to figure it out at a glance without doing any calculations. So here is the proportional abundance on the y-axis, and here's the number of species on the x-axis. And look, if we have species here on the x-axis, we can simultaneously figure out the richness, which is the x-axis, and the evenness, which is the slope here. So here's some real examples from the real world. Okay, here's 2 fish communities from the central Gulf of California and the northern Gulf. Look, steeper slope in the northern Gulf. It's less diverse. It's because it's less even. Shallower slope in the central Gulf here because the fish species are more even. And also, look, there's a little bit greater richness. So you get about 57 species in the central Gulf and only 53 in the northern Gulf. Central Gulf has more richness, but it's also more even because the slope is shallower. Here's a more dramatic one for, let's see, these are invertebrate communities. And so here you have the blue line, and this is in coastal ponds. And look, a few species dominate the communities of coastal ponds. And notice that you don't have very many species. So low richness, and also the slope is very steep, low evenness. In mountain streams, look, very shallow slope, and there's a whole bunch more species. So you can quickly extract information about both richness and evenness without doing calculations. That's why people like these rank abundance curves. Okay. So you will see these practice things on Moodle, and I will expect you to be able to interpret them on the 4th exam. That's all we're going to do today. We will have food webs on Monday in a pre-recorded presentation, and then we'll have Succession on Wednesday, once again live. So unless we have questions in class or questions at home, we are done for the day, maybe even a little early, and you're welcome. Yes, question here. Wednesday, we will be back here in person. I'll be broadcasting on Zoom. Monday, nobody is to come because I won't be here. All right. Thank you. Great. Okay, everybody at home, any questions at home? All right, then. We'll see you either today for lab or we'll see you Wednesday.